Hey everyone. In this video, I'm going to go through two examples of probability distributions, and we're going to characterize them using the measures that we talked about in the previous videos. Okay, so we're going to look at one discrete random variable and one continuous random variable, and we'll talk briefly about the probability density and mass function, the cumulative distribution function, variance, standard deviation, and so on. And I'm going to also talk briefly about how to work with these distribution functions in R. Okay, so the first example for a discrete random variable is the binomial distribution. And as you remember from last semester, maybe, is that the binomial distribution is a generalization of the Bernoulli distribution, right? So the Bernoulli was just one coin flip, either heads or tails. And now, instead of just flipping a single coin, we now consider an experiment in which in which the same coin is flipped independently and multiple times, right? So in other words, a binomial random variable, which we could denote x, records the number of successes in a total of n independent trials with success probability p. Okay, and it is, in other words, it is you could think of it as the sum of n independently and identically distributed Bernoulli variables. Okay. So how can we specify the probability mass function? Remember, it's a probability mass function because this is a discrete random variable. And we can specify for the probability mass function for some random variable x that has a range between 0 and n for the number of successes between 0 and n for n trials. Okay, the probability of x being equal to some value x, this is the random variable x being equal to some realization x, is equal to n choose x times p of x, p to the power of x times 1 minus p to the power of n minus x. And just to go through the underlying logic, p is the success probability, x is the number of successes, right? So we have p to the power of x, so that's p multiplied by itself x times for those x successes, and 1 minus p is the probability of failure, and of course those are the remaining n minus x trials that were not successes. Okay, and we cannot just multiply those two probabilities together, or p to the power of x times 1 minus p to the power of n minus x, because we have to take into account all the different possible kind of orderings that we could have for successes and failures. And in order to take that into account, we multiply this by this binomial coefficient n choose x. Okay. The cumulative distribution function is then just, of course, the sum of all these probability mass functions for k equals 0 up to x. Okay, and then we, of course, have replace the x here with our k indicator. Okay, so that's just the sum of all individual probabilities up to x. Okay, oopsie. Based on this probability mass function and the cumulative distribution function, we can specify the expectation of x as n times p. We could just multiply, we could just plug in n and p and multiply this out, and we would get our value n times p for any binomial random variable. And the same thing for the variance, n times p times 1 minus p. Okay, this holds for any binomial distribution with n trials and success probability p. So as soon as you have a binomial distribution, and you know the number of trials, you know the success probability, you can compute the expectation and the variance of that probability distribution. Okay. We can also plot this binomial distribution. For example, here we have a case where we flip a fair coin with success probability 0.5 3 times. We could plot the probability mass function, which again, basically for each possible outcome of x, which now ranges between 0 and 3, we can directly compute the probability for each of those outcomes. Okay. The cumulative distribution function is then basically the sum of those individual probabilities up to a certain point. So up to x being equal to 0, the probability is, of course, or for 0, the probability is 0.1, something lower than 0.1, and then for x being larger or equal, or no, x being smaller than 1, we have a probability of, I don't know what that is, 0.155 or 14 or something like that. Then we have, that should just be one half yeah, exactly. Sorry. And then for x being smaller than 2, we have the probability being approximately 0.5, and so on. So this is the probability of x taking a value that is smaller or equal to a certain point. Okay. In general, so in one of your assignments, you'll have to work with these probability distributions, not the binomial distributions, but other types of distributions. There are, other discrete distributions like the Poisson distribution, negative binomial, and so on. And in general, if you're working with probability distributions in R, there's a certain kind of structure in how R allows you to work with these probability distributions and probability functions, okay? And basically the way this works is that probability functions in R always follow the same command structure. There's a prefix and a distribution name, right? And so depending on what distribution you want to work with, you first figure out kind of the distribution name, and then figure out what exactly you want to do with that distribution to kind of find the appropriate command, right? If you want to draw random numbers from a distribution, that prefix is R. If you know a certain value of x and you want to know the density at that point for a continuous random variable, that's a density. For the discrete random variable, that would be directly probability mass, essentially. That's D for density. If you know x and you want to know the probability up to that point, so that's kind of the cumulative distribution function, the prefix is P. And if you know the area and you want to know the x value up to which, basically up to which you have to integrate to get to that probability, you use Q. So that's kind of the reverse of the previous one. So how does it look in R specifically? Going back to our binomial distribution, say we toss 2 coins 1,000 times. The sample space is, of course, 2 heads, 1 head, or 2 tails. The random variable that we kind of define for this is that heads are counted as 1. So we have 0, 1, or 2 as potential outcomes for this experiment. We can directly now take random draws from that distribution. It's a binomial distribution. We take random draws, so it's R binom right here. 1,000 for the number of repetitions. Size is equal to 2. That's the n of the binomial distribution, the number of trials, and the success probability. And then we can see that we have a frequency table just by looking at the table of the number of times we got a 0, 1, or 2 for this specific random variable. Okay. We could also ask questions like, what is the probability to observe a 0 or 1 or a 2? And this would be, now again, since we're working with a discrete random variable, we can directly look at d binom, which gives us the probability, the value of the probability mass function for these 3 different values, and we have 0.25, 0.5, and 0.25 for those 3 outcomes. We could also examine the probability to observe at least one one het, for example, and keep in mind that p binum gives you the probability of x being smaller than a certain value. So in order to compute the probability of x being larger than a value than that value, we have to look at 1 minus p binum, um, um, and we look at q being equal to 0. So that's kind of the cut point. Again, for a binomial distribution of size 2, so 2 trials, and the success probability of 0.5. Okay. All right, now moving on to the continuous random variables, we will look more closely at the normal distribution. And the normal distribution, as we talked about in the past, is kind of one of the most important distributions in statistics because ultimately it helps us describe the sum of many random variables. So given the central limit theorem, and we're going to talk about this a little bit later in more detail, the sum of many random variables from the same distribution tends to follow the normal distribution, even when the original distribution is not normal, right? So we can have a lot of, even unknown distribution shapes, but if we're looking at the sum or the average of those distributions over a large number of observations, then we know that the average or the sum follows a normal distribution, right? And that helps us quantifying uncertainty using the central limit theorem, okay? So that's why the normal distribution is extremely important in statistics, because it helps us ultimately, based on the central limit theorem, to characterize uncertainty from a frequentist perspective over repeated samples. Okay. The probability distribution and the cumulative distribution, the probability density function and the cumulative distribution function are as follows. They're a little bit more complicated than the binomial distribution. And the important thing to keep in mind is that the cumulative distribution function doesn't have basically like a closed analytical solution, but ultimately we have to either look at probability or normal tables for specific values of x, or we just use R to compute given probabilities for this integral under the Gaussian, the bell curve that describes the normal distribution. Okay, but despite the fact that the PDF, the probability density function, and the cumulative distribution function look quite complicated, there's a nice thing about the normal distribution, which is that the expectation is simply equal to mu, that is this mu up here, and the variance of x is equal to sigma squared. Okay, so despite the fact that the probability density function looks maybe a little bit intimidating, we can just keep in mind that a normal distribution has some expectation mu and a variance of sigma squared. Okay, yeah. Okay, let's see. We often also talk about a standard normal distribution. A standard normal distribution is simply characterized by the fact that it has an expectation of 0 and a variance of 1. Okay. Here are a couple of examples of probability density functions and cumulative distribution functions for normal distributions with varying means and standard deviations. I'm not going to go through this in all that much detail, because in one of your assignments you have to kind of recreate some of those plots yourself. So you can kind of play around with different specifications for the expectation and the standard deviation. Okay. There are a couple of important properties of the normal distribution that I want to go over briefly. First, if we have a random variable x that is normally distributed with a mean or expectation of mu and a standard deviation or a variance of sigma squared, then we can specify, then we know that some random variable z, which is just x plus a constant, is also normally distributed. Okay, so that means adding a constant to a normally distributed random variable is still normally distributed with just a new expectation, which is mu plus c. Okay. Similarly, if we multiply a random variable times a constant c, then the new random variable is still normally distributed, but now we have a new expectation, which is c times mu, and we have a new variance, which is c times sigma squared. Okay. Both properties together that we can that kind of adding constants and multiplying by constants yields the same, still yields a normal distribution, but with varying means and standard deviations, implies that the z-score over a normal random variable follows the standard normal distribution, right? And this is kind of the underlying logic that we rely on when we compute z-scores, which is standardizing by subtracting the expectation and dividing by the square root of the variance, or dividing by the standard deviation. Based on these properties, we know that normalizing a random variable by subtracting the expectation and dividing by the standard deviation implies that this new z-score this new random variable that is standardized now follows a standard normal distribution with mean 0 and standard deviation of 1. Okay. Another important property is if we have two random variables that are normally distributed, x and y, with separate different means and different standard deviations, then the sum of those two random variables is also normally distributed. Okay, so and the expectation of that new random variable is equal to the sum of the expectations. Okay, again, following the same rules with regard to constants that we talked about before. Okay. Similarly, when we look at the variance of that sum of random variables, we have to take into account that the variance of the sum is equal to the sum of the variances, and we have to account for the constants the same way we accounted for constants previously with variance, which means we can pull them out, but we have to square them. A squared times variance of x plus b squared times variance of y, and the c that was added here of course drops out, right, because the variance of a constant itself is just equal to 0. Okay. More generally, if we have a number of n independently distributed random variables that are all normal with the same expectation and the same variance, then the sum of those normally distributed random variables is again also normally distributed, where the mean is just n times the expectation of x and the variance is just n times the variance of x. Okay. Kind of related to this argument of z-scoring that we talked about, another kind of important property of the normal distribution to keep in mind is that if the data are distributed according to the normal distribution, about 2/3 are within 1 standard deviation from the mean, and approximately 95% are within 2 standard deviations from the mean. To show this, we can consider the probability that a random variable with mean mu and standard deviation sigma lies within k standard deviations from the mean for a positive constant k larger than 0. Okay, so kind of to go through this step by step, if we consider the z-scores for the probability of some random variable x being between mu minus k times sigma and mu plus k times sigma. So mu is the expectation, and we're basically looking at the probability of x being k times sigma below the mean and k times sigma above the mean. We can then simplify this by subtracting mu on both sides, and then this becomes minus k sigma is smaller equal x minus mu smaller equal k times sigma. And then we can divide by the by sigma to ultimately get the z-score here, x minus mu divided by sigma. Again, that's the z-score that we talked about in the previous slide. And we have the lower bound of minus k and the upper bound of k. So in other words, we can now specify this as the probability of minus k is smaller than the z-score is smaller than k, which we can separate as the probability or the cumulative distribution function up to point k minus the cumulative distribution function up to minus k, okay? So we can directly compute this to kind of verify that 2/3 are within 1 standard deviation and 95% are within 2 standard deviation, to then compute using p-norm based on a standard normal random variable. Plus or minus 1 standard deviation from the mean is around 68%, and plus or minus 2 standard deviations from the mean. So that's, plugging in this f of k minus f of minus k. It's p norm 2 minus p norm minus 2, and that's 95%. And in the next example, I'm going to show that visually as well, to kind of visualize how this normal distribution looks like, okay? As I mentioned, the normal distribution is so important because we can use it to describe the sampling distribution of random variables, or of the expectation of random variables, irrespective of how what the underlying distribution of the random variable itself is, because we know for a large number of observations the sum, and by saying that the sum is normally distributed, we also know that the mean is normally distributed. We can directly kind of specify the shape of the sampling distribution for large sample sizes. Okay, and that's what ultimately the central limit theorem allows us to do, right? So just as a quick wrap up. The central limits theorem can be specified as follows. Suppose that we obtain a random sample of n IID observations. IID, again, is independent and identically distributed x's that are all from a probability distribution with mean e of x and variance of x, okay? We can denote the sample average as xn bar, which is 1 over n times the sum from I equals 1 through n of xi, okay? So this is just the average over all xi's, okay? Now we can compute the expectation of that xn bar by just plugging in the expectation or the formula for the sample average, and then kind of simplify this, pulling out the constant, pulling out the sum, and then we get the expectation of x. We can also compute the variance of x bar across these n observations, and that just turns out to be 1 over n times the variance of x, because again we pull out 1 over n, that's 1 over n squared. We can pull out the sum, so that's n times the variance of xi, so 1 over n squared times n times the variance of xi turns out to be 1 over n times the variance of x. And based on that, and based on the central or based on this specification of the expectation and the variance of x bar, the central limit theorem now says when n is large, we can say that xn bar itself is normally distributed with exactly the expectation e of x that we computed here, and the variance of x divided by n that we computed up here. And the key thing is that this, no matter what the underlying distribution of x itself was, we know that xn bar, so the average over those observations, follows a normal distribution as long as n is large enough, okay? And now, since this is a normal distribution with a given mean and a given standard deviation, we can, just following the same logic, compute the z-score, subtracting the expectation, dividing by the variance, plugging in those numbers, or plugging in those expressions, and that z-score is then follows a standard normal distribution, and that's, that helps us, directly kind of specify hypotheses tests, from the frequentist perspective, using the central limit theorem. Okay. Just to remind you, I went through a lot of material fairly quickly. Make sure if you need more details to check additional, for example, examples of simulations of like discrete probability distributions and continuous probability distributions in the last semester's 701 videos on probability theory, uncertainty, and hypothesis testing. Okay. All right, so that's our overview of kind of the key mathematical and concepts in probability theory. In the next video, I'm going to go through one coding example from the book focused on height, weight, and normal distributions.